We have Nicole Morlica to speak here today. Nicole got her PhD at MIT a little under 2 years ago.
Although 2005, yeah.
I've never seen the diploma, so that's only hearsay anyway. I actually had the pleasure of meeting Nicole at a workshop in Italy. That was a nice place to have a workshop, I must admit. So she's going to speak to us today about her view of AdWords.
There's not just AdWords, you know. There's also Ad Center. And
It's your talk. Talk and load.
Okay. So I'm going to be talking about the challenges in the design of sponsored search auctions. So in 1994, we saw the first online advertising in banner ads for Zima and AT&T, and they appeared on hotwire.com. They were sold in pay-per-impressions system. And they were, quite successful in bringing the idea of monetization to online services. In '96, we also started to see some affiliate marketing. These are the ads for like Amazon and CD Now and sites like that, where they post ads for a particular product on a host web page, and then when somebody buys this product, they pay the Amazon or CD Now or whatever, pays some percentage back to the host web page. Then finally in '98, GoTo.com developed the first pay-per-click advertising systems. And these were ads for text-based ads on search web pages, and they were adopted by Google in 2002 with some slight differences in the selling mechanism. So in these systems, the advertisers pay only when the user clicks on their ad. It's some kind of pay-for-performance model, and it's a middle ground between the pay-per-impression and pay-per-acquisition schemes that we had seen previously in the industry. And one nice thing about these pay-for-performance models, of which pay-per-click and pay-per-acquisition are one kind of them, is that it provides incentives for the host to improve the ad displays, because the host only gets paid when the ad is successful in some sense. So, as opposed to banner ads, where when users start suffering from banner blindness, as it's called, the host doesn't really care because they're still getting paid. So the other innovation in this scheme was that the advertisements were sold through an auction mechanism where advertisers are bidding on keywords. And this had two huge advantages. One is that it allowed for increased targeting opportunities because you could specify what sorts of keywords you wanted your ad to appear on. But another big benefit here was that it really made a low barrier to entry for a lot of the sort of mom and pop shops that were on the internet. So you have all of these very small businesses. They can't afford to negotiate contracts for banner advertising with the host web pages, and so the auction mechanism was quite easy for them to use, and they could start to have online ads as well. So I want to talk about this market design of the pay-per-click advertisings, and in order to do that, I want to introduce to you what I assume is a general framework for what the three major players in this market are using these days, being Google, Yahoo, and MSN. So we have a web page. Let's focus now on search. And so whenever somebody searches for a keyword, we get some algorithmic search results, which appear underneath the keyword. And on the right-hand side, or sometimes underneath or above the algorithmic search results, we get some ad slots. And it's these ad slots that are sold through the auction mechanism. I'm going to describe the rules of the auction as I'm going to assume them to be for the rest of this talk through the use of an example. I have here 2 ad slots and 3 advertisers. And I say that these 3 advertisers are interested in being shown along with this keyword. And each advertiser submits to the search engine the amount that they're willing to pay for a click that they receive after a user searches for this keyword. So in my example, advertiser A has $10 value per click, B has $5 value per click, and C has $50 value per click. Additionally, each advertiser has an associated click-through rate, which the search engine learns. It's some parameter that the search engine learns over time, and I think these days people are starting to call these quality scores. But basically, the click-through rate is some estimate of the probability, at least the way I'm going to think of it, is it's an estimate of the probability that this user will click on that ad. And then the search engine takes the bid times the click-through rate of each advertiser. Now, this can be interpreted as the expected bid per impression. It's how much it's worth to the advertiser to be shown on the search page. And it then allocates the ad space in decreasing order of this expected bid per impression. So here, advertiser B, who actually had the lowest bid per click, anyway has the highest expected bid per impression and is shown in the first ad slot. Advertiser A is shown in the second ad slot, and advertiser C is not shown because I'm assuming that I had just 2 ad slots in this search engine page. So now this is the allocation scheme. I also need to, in order to specify the mechanism, I need to define the pricing scheme. So what the search engine does is some sort of quote-unquote second price auction. And what do I mean by that? I mean that I'm going to charge each advertiser, when they receive a click, I'm going to charge each advertiser the minimum amount that he would have had to bid to maintain his position in the ranking. So here, for example, when I have a click, let's see how much I'm going to charge advertiser B when he's clicked on. His closest competitor in the ranking is advertiser A, who has a bid times click-through rate of 1. And advertiser B's own click-through rate was 0.5. So by taking the ratio of these two numbers, I see that so long as B bid at least $2, he would have maintained his position in the ranking, and therefore I charge him $2 per click. I can similarly calculate the per click price of advertiser A. It will be $5, and advertiser C is not shown, never clicked on, and never charged, for this search at least. So this is the general framework I'm going to explore in this talk, and there are many challenges that are introduced by this market design. For one, we need to think about what is the right bidding language for these advertisers. So currently, we're asking advertisers, how much do you value each click, and what's your maximum budget? Is this really, are these the questions that we should be asking? Should we allow the advertiser to have more expressivity? I learned earlier today that in Google, you're now allowing advertisers to bid on which slot they want on the search page. So that's an example of making the bidding language more expressive, and it might enable the advertisers to more accurately reflect their true utilities, but it also might introduce complications in the auction scheme and reduce the transparency of the auction. So it takes a lot of thought to figure out what is the right bidding language. Another interesting question is, what is the right product to sell? So here in the market, as I've described it, we're selling clicks. That's our product. So why should we sell clicks? We had seen before people were selling impressions and people had been selling acquisitions. Should we be selling impressions or acquisitions or some combinations of clicks, impressions, and acquisitions? So this is another thing we need to be thinking about. Then we have to think about how we can compensate the eyeballs. So far in this market, we've been thinking about this as a market for advertisers. And the players in this market are the advertisers and the host websites, the search engines, for example. But there's a third player in this market that's actually extremely important to the success of the market, and that's the eyeballs of the searchers. And this is essentially what we're selling. We're kind of, if you like to think of it this way, exploiting the users and making money for us by showing them these ads. And it's not exactly exploitation because we're giving them the product, free web services as a compensation, but is this really the right compensation? Should we perhaps additionally give them some monetary compensation? Finally, there's...
That was the whole point of keyword-based advertising, was that there's some assumption that the user is actually interested in that ad.
Yeah, we can make the user more interested in that ad if we give him some discount on the product that he might buy by following through with the link. Imagine, for example, if you click on this ad, we're going to give you some coupon for the product that the advertiser sells. This will incentivize the advertisers to produce more relevant ads. So another thing that I want to think about is how can we use stochastic information in the allocation. So the auction framework that I presented is that every time a keyword comes, I run this auction, and this auction is run blind to the fact that future auctions will be run for the same keyword, or that past auctions had been run for the same keyword. And in fact, search engines have a very good idea of how many searches there are for any particular keyword in any given day from historical data. And shouldn't we be using this information in a more direct way when we figure out how to run the auction for each particular word? In fact, why are we running these auctions per word? Why don't we run them at the beginning of the day and sell all the supply we have in an offline setting? And we all know that offline algorithms are much more efficient than online algorithms. So understanding how to use stochastic information in the allocation is also related to the idea that we can try to introduce mechanisms that guarantee the supply for the advertisers. So we can sell an advertiser like 100 clicks, and we can guarantee that he'll get 100 clicks. And if we allocate to him the number of clicks we promised, we can try to reimburse him. And this more directly mimics the systems in place for banner advertising. And it also could be attractive to advertisers as a way of eliminating risk. So I'm not sure that this is the right direction to go per se, but it's an interesting thing to think about. Finally, so these are all just vague ideas that I've had about this market design, and I mean, many other people have had about this market design. The things I want to talk about in more detail today are the issue of click fraud and the complications that arise from the fact that advertisers have budget constraints. So let me start with click fraud. What do I mean by click fraud? That's the act of clicking on an ad with the sole intent of increasing or decreasing the spending of an advertiser. And it's been in the media a lot, and is clearly a serious problem with these pay-per-click systems. Why is it a problem with pay-per-click systems? An advertiser is charged only when a user clicks his ad, and so a fraudulent user may click on ads just to increase the spending of an advertisers. And since each click costs on the order of $1, of course this figure varies a lot across keywords, but $1 is a sort of typical cost. This means that 1 million fraudulent clicks are going to cost the advertiser $1 million. And it's very easy to generate 1 million fraudulent clicks. You can write a simple script. I'm sure anyone in this room could go home over the weekend and write a simple script to go out and click on ads. You don't have to be smart to do this, as evidenced by the second bullet here, that a California man wrote some simple script to click on ads and told Google that they should show up in his garage and pay him $1 million, or he was going to release the script. And so at the appointed time, the FBI showed up in his garage and arrested him. And it's also true that scripting is not the only way to generate click fraud. It's becoming increasingly common to see that companies hiring people in second and third world countries, typically India and Eastern Europe, to just sit at home and click on ads. And this is a great source of income for them. Since the ads cost the advertisers about $1, these people, when I was doing this literature search, they were being paid about 20 cents per click to go click on an ad, spend 90 seconds on the target website looking around at the product that the advertiser was selling. And they were happy to do this. They could sit at home, do this with their kids on their lap. So, you know, there's a lot of click fraud that's being generated. How can we hope to combat this fraud? Currently, the one main technique for doing this, at least we assume so in the academic literature, is through machine learning. So we automatically try to detect and discount frauds, and this could be, you know, double-checked by humans and so on. These techniques are, you know, somewhat successful, but they have possibly high classification error, and they're also quite susceptible to the India model attack because it's rather difficult to distinguish between a human committing fraud and a human that's really shopping online. It's possible, but they look pretty similar. Another proposal for reducing click fraud that's been talked about a lot in the literature is to change the market model. This is really an issue with the fact that we're selling clicks. So why are we selling clicks? Why don't we sell per impression? Maybe we can still keep some of the benefits of the per click models on selling per impression if we, say, do it along with an auction. Also, we could sell on, Goodman proposed in the sponsored search workshop in 2005, selling per percentage. So you can buy 100% of the keywords for blah should show your ad, or say 50% of the keywords your ad will be shown. So while these models do reduce the possibility of fraud, they are a departure from a developed industry standard and are likely to be met with resistance by the advertisers. And then they also lose some of the benefits of the developed industry standard. So in a recent paper, what we did was we tried to come up with a way to reduce click fraud by changing the way that the auction is run. Sort of behind the scenes. And the reason that we had some hope of doing this is the following observation, that each fraudulent click, it incurs a short-term loss, which is due to the cost of the click. But it also gives you a long-term benefit because it increases the search engine's estimate of the click-through rate. And the price of future clicks is inversely proportional to the click-through rate. So what we do is we propose a class of CTR learning algorithms in which these effects cancel, and thereby click fraud is reduced to impression fraud. You can't cost an advertiser more than you could cost him by creating false impressions in an impression-based system. So in order to explain this work in more detail, let me first define what I mean by a CTR learning algorithm. There's many ways you could imagine estimating the probability that an ad receives a click. You can look in the history, the last 100 hours, count the number of times that you showed this ad, and count the number of times that you showed this ad and it got a click, and take the ratio of these two numbers. You could look at the last 100 impressions and look at the number of times that this ad received a click, divide that by 100. You could look at the last 100 clicks, count how many impressions did it take for the ad to receive these 100 clicks, and take 100 over that number. Okay, so these are just 3 examples of learning algorithms. You can come up with many more yourself, I'm sure. In order to define a general class of which these 3 learning algorithms are examples, let me introduce some notation. I'm going to label the impressions, starting with the most recent, by 1, 2, up to n. And I'm going to let Ti be the amount of time that elapsed after impression I. Ci is the number of clicks that were received after impression I. And Xi is an indicator variable that the ith impression got a click. Okay? So then I will say an algorithm is a CTR learning algorithm if it's parameterized by some discounting function, delta, which is a function of these 3 parameters, the time since the ith last impression, the number of clicks since the ith last impression, and I. The CTR learning algorithm is simply the weighted average over the impressions of the number of clicks. Okay? So in this formula here, you see that I can use it to express all the 3 learning algorithms I proposed in the previous slide. The averaging over a fixed time window, you just simply set this discounting function to be 0 after the time Ti is larger than your time window T. And you can check that the other 2 algorithms can be represented with this kind of formula. So the first observation is that for appropriate parameters, all 3 of these algorithms estimate the true click-through rate to within an arbitrary accuracy on a random sequence of clicks generated from a constant CTR. Okay, so if we have a scenario without fraud, let's assume that the true click-through rate, the true probability that an ad receives a click is constant. If I have a long enough sequence of random experiments in which I'm showing this ad and this probability of receiving a click is constant, all three of these algorithms are going to be able to estimate this true probability. And when that happens, the system behaves exactly like a pay-per-impression system, which is what we want. So this brings up the question, does that mean that all of these algorithms are equally resistant to fraud? And in order to answer that question, I first have to tell you what do I mean by fraud. When do I say an algorithm is fraud resistant? I say an algorithm is fraud resistant if a scammer cannot significantly increase the average price per impression of an advertiser in a scenario with fraud as compared to a scenario without fraud. Okay, this is intuitively what I mean. For the exact parameters of what significantly is and things like this, you can look at the paper. Basically, what I mean is that, what I'm going to assume in the rest of this talk is that I have just one slot with a reserve price P. Okay, and I'm not considering the kind of fraud that causes an advertiser to fall off this slot. I have just one advertiser, it's always going to be shown in this slot. Can I generate a sequence of clicks on this advertiser to increase his price per impression beyond P? And so the answer is that no, not all algorithms are equally resistant to fraud. In order to see that, you can, this is just going to be a sketch of an idea of how to scam the following algorithm that averages over the last 10 impressions. When there's no fraud, we convert, each of these impressions to a click, represented by a green line, with some constant probability, and the estimated CTR, according to this algorithm, is going to be constant. But a scammer can come along and insert a bunch of fraud uniformly at random, represented by red lines here. And in bursts, he's going to convert parts of this fraud to clicks, and parts of it he's not going to do the click. And this bursty behavior is going to cause the estimate of this CTR to vary over time. If you use this basic intuition and do the math, you'll see that this is going to cause the advertiser to actually spend more money per impression than he did in the scenario without fraud. This is for that particular algorithm that was averaging over the last 10 impressions. I'm going to say that an algorithm is click-based if this discounting function, delta, depends only on the number of clicks after impression I, that variable I was calling C sub I. And what we prove in a paper in Wine 2005 is that click-based algorithms are fraud resistant. So the proof is by a charging argument. And I think I'll skip the proof, and we can come back to it if we have time at the end of the talk and you're interested in actually seeing the math details. But let me, for now, one more last thing I wanted to say about the click fraud work is that it gives you a way to try to implement a pay-per-acquisition system in a manner that incentivizes advertisers to truthfully report their acquisitions. We can define an acquisition rate of an advertiser. Yeah?
So when in the statement of the result that the thing is fraud resistant, does it say that the advertiser doesn't have to pay more on episodes where there were not fraudulent clicks due to the effect of the clicks on the estimates of the click-through rate? Or does it also include the cost of the actual fraudulent clicks? You see what I mean? There are two possible sources.
So the thing is that you don't pay more per impression in a scenario with fraud than without fraud. But in the scenarios with fraud, there are more impressions. And yes, so you're going to pay more because of this factor. But that's exactly what I mean by saying that it's reducing click fraud to impression fraud. You're not going to be able to cause the advertiser more expenditure than if you had been selling per impression and the guy was creating impression fraud. Does that make sense? So we can use these techniques to develop a pay-per-acquisition system where advertisers have an acquisition rate. We rank advertisers in order of their acquisition rate times their bid per acquisition, and we learn the acquisition rate using an acquisition-based, I guess it would be ATR Learning Algorithm. So exactly everything I've just said now about clicks, you can say about acquisitions. So if there are no more questions about the click-based work, I'll move on to the budgets work. You still seem suspicious.
I'm afraid I may not understand the impression fraud idea after all. So do you count an impression as any time there was an opportunity to click on an ad?
Yeah, so by impression I mean the appearance of an ad, and it can be both an impression and a click if the impression converted to a click.
So why are there more impressions when there's...
I'm looking at one scenario. I have one history in which was generated according to this random process where ads were clicked on with some fixed probability. And then I'm allowing a scammer to come along and insert extra impressions, which he can then either click on or not click on. So this is going to create extra impressions. I mean, you saw this in this example here.
So I would imagine that impressions would be cheaper than clicks. Is that right?
Yeah, impressions cost. So I'm thinking that the click-through rates are on the order of 1%. So, and the cost per click is on the order of $1, so impressions costs kind of like 1 cent. So you can't, for example, pay someone 20 cents to create false impressions. That's one reason that it's...
So one thing that's confusing a little bit is I'm imagining a scammer that creates a 1% increase in the number of impressions, which would result in 1% increase in the cost if you were paying per impression, but clicks on all of them, and so that would double the number of clicks, right?
Oh, but if he clicks on all of them, the cost per click is going to become very cheap for the advertiser because the estimate of the click-through rate is going to skyrocket. And we're capitalizing on this to prove that in systems, if you learn the click-through rate appropriately, you're going to track the fluctuations at exactly the right rate in order to discount the fraud. So let me move on to the bidding with budget constraints work. So let's talk about budget constraints. Advertisers have a utility VI per click, and per click per keyword. Let's just focus on one keyword for this definition. Okay, so they have a utility of VI per click, and they have a hard budget constraint BI on the amount they can spend in one day. And what does this really mean in terms of the utility of the advertiser, the happiness of the advertiser for his allocation and price? What I'm assuming it means is that if the advertiser receives J clicks and his price is P, his utility is going to be J times his value per click minus P, so long as this price P is less than his budget constraint. But if the price P exceeds his budget constraint, his utility is going to be minus infinity. Okay? And of course, I can generalize this to multiple keyword setting. Now,
so what is I there?
I is the advertiser. So, how can I design an auction setting for bidders with budget constraints? A very standard technique in auction theory for designing a truthful auction is called the VCG mechanism. This mechanism chooses the allocation which maximizes the social welfare. The social welfare is simply the total value that all the bidders have for the allocation. Okay? So in this case, if you want to maximize the total value of all bidders for the allocation, you should simply give all clicks to the bidder with the maximum value. This would be the welfare maximizing solution. But by individual rationality, we can charge each bidder at most his budget constraint. Otherwise, he's going to walk away from our auction with infinite negative utility. And this means that the VCG auction in this case is not truthful, because you can just, if this was your auction, give all the units to the person with the highest value and charge them at most their budget constraint, you of course would come in and you would say your value is infinite and your budget is 0, and you're going to get all the clicks. This is not very surprising because VCG is truthful precisely when the utility functions are quasi-linear, which means that they're linear in this price parameter. And you'll notice that this utility function is not linear in this price parameter because when the price just exceeds b, the utility jumps to minus infinity. So we could try to circumvent this problem. A natural way to do that would be to cap the welfare of a bidder to be his budget constraint. So if your value is infinity, but your budget is 0, I'm not going to allow you to have more than a 0 welfare for that allocation. And again, this modified algorithm, modified VCG I call it, is not truthful, even if the budgets are public knowledge. So let's go through the example. Here I have 2 bidders. Bidder 1 has value of $10 for each of these objects, but has a budget constraint of $10. And bidder 2 has a value of $1 for each of these objects and a budget constraint of $10. Now, according to this modified definition of welfare, the welfare maximizing solution is to give 1 unit to bidder 1 and 1 unit to bidder 2. This gives you a total welfare of $11. The sum of the valuations of the bidders for this allocation is $11. I haven't told you how VCG computes the prices, but if you were to compute the prices, you would see that the payment of bidder 1 is $1 and bidder 2 is $0. And thus the utility of bidder 1 in this scenario is $9. Now, if we change this setup and bidder 1 just lies about his value and says his value is actually $5 instead of $10, now the welfare maximizing solution will give both units to bidder 1 for a total welfare of $10. And again, you can calculate the payments and see that the payment would be $2, and thus his utility is $18, which is more than it was in the previous setting. So he has an incentive to lie here. And this begs the question if there is any truthful mechanism for bidders with budget constraints. Maybe, this was just the wrong mechanism. In fact, we can show that there is no truthful mechanism which satisfies 3 properties that are, you can argue about how reasonable they are, but there are things that you might want to assume about a mechanism. I don't want to go into detail about what they mean here. But this is a pretty strong negative result. We can also give a accompanying positive result, which is a truthful auction which maximizes the revenue by breaking some of those natural assumptions. Let me tell you what the mechanism is. It splits the bidders randomly into 2 groups, A and B, and it computes the optimal price, PA, of selling at most half the units to the bidders in A. And it's, again, similarly computes a price PB, which sells at most half the units to bidders in B. So what do I mean by optimal price? I mean, if you were going to sell all these units at a fixed price, what price would you set in order to maximize your revenue? Okay, so here I've defined these 2 prices, PA and PB, and I'm going to sell my units at a price of PA to the bidders in B and at a price of PB to the bidders in A. So you can't affect the price that you're offered by changing your bid. And furthermore, I'm going to sell these units in a arbitrary order to bidders. So I'm gonna offer, say, Kevin, here's the price. How many units do you want? And I'm just going to go around the room in order and sell the units, however many units each person wants, at this fixed price until the units are all gone. Okay, so you can't affect how many units you'll be offered by your bid either. Therefore, the mechanism is truthful. Why is it not satisfactory? Well, first, let me state the result. The mechanism is truthful, and it generates close to the optimal posted price revenue. So if you were going to sell all M units to all the bidders and you knew all their valuations and you didn't have to worry about truthfulness, how much money could you make at a fixed price? That's what I call opt. And this mechanism gets close to that opt, so long as the maximum budget of any particular bidder is small. Okay. What is not satisfactory about this mechanism is that you can't guarantee any allocation even by increasing your bid. It could be that you're, last in the lineup, and everybody else, by their fixed bids, are winning particular amounts, such that by the time the auction gets to you, there are no units left over. And even if you're bidding infinity, you're not going to win anything. And this is violating the first of those assumptions I said in the last slides, consumer sovereignty. Yeah, it also violates some other things, but this is one very negative property of this algorithm. Another thing that's kind of frustrating, so this is a very common technique in auction design, this random sampling it's called. Another frustrating thing about these algorithms is they usually are dual priced, and they offer one price to half the people and another price to the other half of the people. And psychologically, that kind of pisses off people in the half that's getting the bigger price.
What does small mean, the last small mean there? Where the maximum budget over the optimal revenue is small?
This is going to be some parameter epsilon in the probability that the mechanism generates this revenue.
And the relationship to delta?
I don't remember the exact relationship.
So, for example, if you have a market in which there are only two suppliers, then is this a viable assumption?
Two suppliers? No, this is an assumption about the bidders' budgets, right? So the question is it reasonable to assume that that I'm not giving you all your revenue? If you have just one company, like say eBay, that's contributing half the revenue of AdWords, that's a problem for this mechanism. But if all of your players in the market are pretty small, no single person has too much power, this theorem is going to go through. And the reason that you need something like this is because if I have, a very high value and a very high budget and compared to everybody else, the optimal posted price mechanism is going to be able to extract all of my budget because it knows I can't lie to it, right? The optimal posted price would be to charge me my value and get all of my budget. But truthfully, you can't hope to do that because clearly I could always pretend to be much smaller than I am. So you need something like this, and all of these random sampling auctions have some assumption that has this kind of flavor. That's not why I mean, I think that's a reasonable assumption. I don't think that's why it's not used in practice.
Yeah, but for some markets, it could be that there's just very few people who are actually interested in purchasing that, and the budget for a given advertiser may actually be fairly close to what the total revenue derivable from that is.
Yes.
In which case, that assumption wouldn't be valid anymore.
Yes, that's true. You need to use these in markets where there's a lot of demand and fixed supply. Yeah. Okay, so those previous slides demonstrated that there's a lot of complication in actually designing the auction when bidders have budget constraints. There's a lot of things we need to take into consideration. There's also budget constraints impose some complications on the bidders on how they should bid. And to see this, let's think about the system that I presented at the beginning of the talk, how bidders with budgets should behave in these AdWords style systems. So I have two keywords. One is popular in that there are a lot of searches for it every day, and another is not so popular. There are some searches, but not too many. And for the popular keyword, there's a lot of advertisers with unlimited budgets and utility of $1 that are interested in that keyword. I also have another advertiser, the yellow dot here, which is interested in both the popular and the not so popular keyword and has a budget constraint of $500 and a utility of $2 for either of these keywords. Now, when I just have everybody bid truthfully in the system, what's going to happen? Well, every time the popular keyword is shown, the budget-constrained advertiser is going to win the auction. Let's assume the click-through rates are all equal. The budget-constrained advertiser is going to win the auction because he has a higher utility than the unlimited budget advertisers. And so he's going to win the auction, and he's going to pay $1 every time, and he's going to quickly run through his budget. This makes him unhappy. On the other hand, if he were to pretend that he is not interested in the popular keyword, he's going to win the not so popular keyword and there's no competitors for that keyword, so he's going to just pay the reserve price, and he's going to exist throughout the whole day. He's going to be much happier, and actually so with the search engine in this case, because we're still making revenue on the popular keyword as well as the unpopular keyword. So how should an advertiser bid for the keywords when he's given his budget constraint? What should you do? This is a discrete separable resource allocation problem, which is well studied in the OR literature, the resource here being the budget of the advertiser. And if we know the price of each slot for each page, then this problem becomes a generalization of knapsack. Okay, so if I know the price of every slot for every keyword, then what I'm trying to do is I'm trying to choose at most one instantiation of each object for my knapsack, the objects here being the keywords, and I'm trying to choose a price level for that keyword such that the sum of the prices fits in my knapsack, the knapsack being my budget constraint, and my value is maximized. So a lot of papers in the literature have looked at this interpretation of bidding in auctions with budget constraints with various assumptions about the knowledge of the advertiser and the dependencies between the keywords and the arrival sequence of keywords. Oftentimes, such bidding heuristics are not good enough because they're not fast enough. That could be one reason. And another reason is that the advertisers often don't have all the information that these algorithms would assume of them. For example, they often have only local information about the prices of various slots on various keywords. They know the price of the slots near them, perhaps, but not all the slots. So as a result, it makes sense to study some simpler bidding heuristics. And here I propose one natural bidding heuristic called the return on investment, equalizing return on investment. What do I mean by this? Well, the return on investment is defined to be the ratio of the utility that you get from an ad divided by its cost. That's the return on investment. And the heuristic is, if your budget is limited, you should try to equalize the return on investment of all your ads. If you're overspending your budget, you should reduce your bid on the ad which has the lowest return on investment, thereby moving your ad down to a lower slot and increasing the return on investment for that ad. If you're underspending, you should increase your bid, up to at most your utility, of course, for the ad that's giving you the best return on investment. By increasing your bid, you're going to move up to a higher slot and thereby increase the price of that ad and decrease the ROI, thus starting to equalize it across all your ads. Okay, so this is the heuristic. It's a pretty natural heuristic. You see when you talk to at least people at iProspect and other SEMs, they say that they're using things similar to this. Oh, I also wanted to mention that this is very similar to the 2 approximation for the knapsack algorithm. In fact, if all of the ads had just one slot, you would be exactly running the 2 approximation to the knapsack algorithm, except that in the 2 approximation at the last step, you sometimes add the ad with the highest value instead of taking the prefix ordering. Here, we're just taking the prefix ordering, for those of you that know the 2 approximation for knapsack. Anyway, so I was saying that SEMs seem to be using this algorithm. It's natural for advertisers to try and use this algorithm. Therefore, we should worry about the equilibrium when everybody is using this algorithm, the system equilibrium. For example, Ad Center wants to offer this as an optimization tool, and many bidders are going to use this tool. And what's going to be the result when everybody's using this tool? What are the prices going to converge to, or will they cycle endlessly? Will the allocations cycle endlessly? Are we going to lose all our revenue if we do these optimizations for the advertisers, or if the advertisers are doing these optimizations themselves? One bad news is that there are examples that don't converge. Here's one such example. I have 2 bidders, okay, and I have 1 item, and these bidders are budget constrained. And on day 1, bidder 1 bids slightly more than bidder 2. At the end of the day, bidder 1 has overspent her budget and Bidder 2 has underspent her budget because bidder 1 was winning all of these ads up to the end of the day, okay, when they ran out of budget. So bidder 2 was winning very few ads at the end of the day. And so on the next day, bidder 1, according to this algorithm, this heuristic, is going to decrease her bid, and bidder 2 is going to increase his bid. And so they're going to change places. And now on day 2, we're going to see the same behavior. So we're going to get this alternation where the bids move up and down throughout the day, and the allocations also move from bidder 1 to bidder 2 on even and odd days, respectively. So this causes cycling in the bidding behavior, and cycling patterns have been observed according to some of the papers in the literature. This is a paper of Zhang, 2006, from the history of a keyword on Yahoo. And you can see when I enlarge that box there that the bids do seem to cycle according to the data that this person had access to. There are many, many reasons for this cycling, and I'm not trying to say that this explanation that I gave is the sole cause of the cycling, but it might be contributing to it. And such cycling is bad. It introduces uncertainty for the advertisers, and they don't like it. And what we show is...
Are the colors different bidders?
Yeah, the colors are different bidders.
What's the time scale here?
This is... I mean, each of these is a different bid. I don't know what the time scale is. The x-axis is the change in the bid.
But this is within one allocation of budget, you think?
Yeah. I don't have access to this data. This is from Yahoo, and this is what I interpreted from that paper. But it could be. You could try to ask Zhang instead of me. So one thing we observe in a paper in this upcoming Dub is that in a perturbed first price auction, this is not going to happen. We can prove this. This is a theorem in our paper. That if you allow the mechanism, the auctioneer, when you take in the bids, what you do is you randomly decrease each bid by a very small amount, okay? And then we're going to run the same sort of auction I was describing at the beginning of the talk, except instead of charging an advertiser the minimum amount he should pay to maintain his position in the ranking, I'm going to charge him exactly his bid, his perturbed bid. So why is this a good idea? Well, if two bids are very close, as in that example I was giving you where the bids were cycling on even and odd days, then the lower bid still has some chance of winning. So we're going to smooth the allocation. We're letting the two bidders share the keyword. When their bids are very close, we should be giving half of the appearances of the keyword to one advertiser and half to the other. Also, this perturbation idea is very useful for a solution for spiteful bidding. Spiteful bidding is scenarios in which an advertiser tries to bid just under the bid of the guy above him in order to cause him to spend his budget very fast. But now if you try to do such a thing, you have some chance of winning the object at a price that's too expensive for you. So in general, I think perturbations are a good thing in auction design, and probably actually because of this CTR parameter, you actually are doing some kind of random perturbation in your auction. I'm not sure exactly what you're doing, but I wouldn't be surprised if you're effectively perturbing the bids because of some other parts of your auction design. So we have this result for first price auctions. We also are able to simulate what's going on in second price auctions and see that, again, the prices and allocation seem to converge to the market equilibrium for a second price auction, but we aren't able to prove that. And that's one interesting thing to do. So here's the simulation for that simple example I was mentioning in the previous slide, where I have two bidders and one keyword, and each bidder has a fixed budget of $500 and a price, a value of $1 per unit, and there's 1,000 units coming per day. Okay. As I explained in the example, you can see from the blue dots that when we don't have perturbations, the bidders each increase their bid to about 0.5. At that moment, they're starting to run out of budget, And so they alternate the allocation on even and odd days. And this graph shows you the bid level of one of the advertisers. It's the same for both advertisers. On the other hand, when I use perturbation, both of the advertisers will increase their bid to $1, and that's their value, so they don't increase it beyond that. And they're not running out of budget when they're bidding at $1 because they're sharing the keyword more or less equally among each other because of these random perturbations. So both the allocation has stabilized and the revenue of the auctioneer has doubled in this instance. So this was just a contrived example. This graph here is trying to get at the fact that this contrived example is not so rare. Here we have, if I recall correctly, 10 advertisers, 20 keywords, 1 slot per keyword. Each advertiser is interested in each keyword with probability 1/3. They have values drawn uniformly between 0 and 1 for the keyword, and they have budget constraints which follow some kind of power law distribution. And when we run the perturbed auctions, represented by the X's and the black X's and the pink stars, we see that the efficiency of the auction stabilizes over time. On the other hand, if we run the first and second price auctions without the perturbations, those are the red diamonds and the blue circles, we see that on even and odd days, the allocation completely changes. So it might look to you like there's 2 lines here for the red diamonds and the blue circles. In fact, there's only one, but it's just zigzagging on even and odd days. And this is because the allocation is switching on even and odd days, and the advertisers on one of those days have higher value for the allocation than on the other. Finally, we have here, we looked at the convergence properties of our algorithms. What do I mean by convergence? I'm looking in that same scenario I described, simulation setup I described in the last slide. I'm running the auction for 300 days, and I'm looking at how many advertisers actually ended up spending close to all of their budget and staying in the auction to close to the end of the day. Okay. And in the first price auction and second price auction without perturbations, in many of the cases, not very many advertisers converged. But when we perturb the auctions, we see that almost all the time, all 10 advertisers converge. So I see I'm already over time, but let me just try to wrap up a little bit. First, about online advertising. I think this market's very interesting and it's still evolving. I mean, it's still quite new, actually, if you think about it. It started really in sort of 98, 2000. As the market evolves, we're going to see more targeted and highly fragmented sales. So each eyeball is going to become almost unique, and we're going to have to figure out how to price these very unique eyeballs. We're going to see increased connections between various media types. We're going to see connections between what you watch on TiVo and what your advertisements you see on your search engine and what you read on your Gmail and so on. There's going to be new revenue sources for online advertising. We've already seen YouTube starting to introduce online advertising. In video games, there's a whole big sort of push for getting some sort of online advertising when you're, say, in a car race game. The billboards you see are some kind of sold through some kind of online auction system. And also, we'll see new sorts of allocation problems. Maybe we can sell ads with particular lengths instead of just one block per ad. You can buy some number of lines of text. I just wanted to briefly mention some of my other research in case any of you get a chance to talk to me and want to ask questions about it. One thing I'm very interested in is social networks, and I've done some work on the evolution of social networks and the diffusion of information and technology in these networks. I'm also quite interested in matching markets, and you Almaden people, I guess, saw me talk about the National Residency Matching Program a few years ago. There's many more matching markets that are being studied these days. There's the kidney exchange, where if you have a donor for a kidney that's failing, that doesn't match your blood type, you can try to exchange your donor's kidney for some other donor's kidney that might match your blood type. And also, you know, AdSense, for example, is some kind of matching program at its heart, because you're trying to match advertisers and websites. So I've done a lot of work on incentive properties in matching markets, and also on the use of stochastic information in these markets. And finally, something I'm very interested in these days are secretary problems. This is or hiring problems. This is, how do you hire the best employee when you need to make your decision online? So these problems have a lot of connections to online auctions, and they're also just interesting online decision problems in their own right. So I've studied these also with the motivation of bidding in ad auctions as in mind. I think that's all I have, so I can take any questions.
They're clapping, you can't hear them.